Hi class, let's do some linear algebra. Today we're going to introduce eigenvalues and eigenvectors. Eigenvectors popped up briefly in when we were discussing motivation for change of basis. Eigenvalues and eigenvectors are fundamental objects associated to a linear transformation, and so are incredibly important. Definition. Say A is an n by n matrix. As usual, a scalar lambda, and here I'm going to make sure to point out that lambda can be complex, is an eigenvalue or a characteristic value of A, the matrix, if there exists a non-zero vector x such that ax is equal to lambda times x. Here, x is going to be called an eigenvector or a characteristic vector belonging to the eigenvalue lambda All right. Let's do an example. Example from a previous lesson. Say we've got the matrix 0.7, 0.3, 0.2, 0.3, 0.8. We showed two vectors associated to this matrix, x1 and x2, which is 2, 3, and negative 1, 1. It just so happens that A times 2, 3 is equal to 2, 3. And A times negative 1, 1 is equal to a half times negative 1, 1. Here I will just highlight that this is 1 times 2, 3, and this is a half. So we've got one eigenvalue, which is 1, with eigenvector belonging to it, 2, 3. And we have a second eigenvalue, a half, with eigenvector belonging to it, negative 1, 1. Here are the eigenvectors, and here are the eigenvalues. Okay. Before we really dive into the algebra of how to find these things, it's really important to develop an intuition for what they mean. Let's talk geometrically. The geometric interpretation of eigenvectors. All right, so we have ax is equal to lambda x, where lambda, probably some complex number. These are the vectors, that don't change direction. Under the linear transformation. Right? A times x is just a scaling of x. They may be scaled. True, they don't change direction, but they may be scaled, and the eigenvalue is the scaling factor. All right, let's explore this. Say we've got the matrix negative 1, 0, 0, 1. We know how to read this now. This is if L is a linear transformation represented by A, this is L of E1 and this is L of E2. All right, let's put this in our graph. Here's a little sketch. It says that if we start with E1, it gets sent to -1, 0, A of E1. If we start with E2, it gets sent to itself. Okay, what does this tell us? This tells us that our linear transformation is reflection across the y-axis. So if we had another vector, say this purple vector, it would be reflected across the y-axis. All right, now that we know what this linear transformation is, let's think about it geometrically. Question: which vectors don't change direction under this linear transformation? Well, I'd like to argue that it's just the vectors pointing in the y direction, as in the span of 0, 1. They don't get moved. Do they get scaled? Question: what is the scaling factor? Well, E2 just gets sent to itself. There's no scaling factor, so the answer is just 1. So here's what we have. We've got eigenvector, for example, 0, 1 or 0, 2, anything really in that span, with eigenvalue 1. Okay, let's do another example to show that it's not always so simple and we might need to get some more tools. Let's talk about rotation by 90 degrees clockwise. Well, we know in general rotation by theta looks like this. So when theta is 90 degrees, this is going to look like 0, -1, 1, 0. And we know what this does. Here's a little sketch. Say this is E1. It gets rotated 90 degrees, and it ends up here, A of E1. All right, so let's ask ourselves the same question. If all of these vectors are being rotated by 90 degrees clockwise, which vectors don't change direction? It seems like the answer is none. No eigenvectors, but the answer is really none with real entries. We're going to return to this example later, so more on this later. We're going to look at complex eigenvalues and eigenvectors. But I do want to give you an exercise. Here's an exercise for you. Say A is equal to 0, 0, 0, 1. This is projection onto the y-axis. You can see it algebraically because this matrix times xy is just 0y. And if we were to do a little sketch, a vector like so would end up here with the action just pressing it into the y-axis. So here's the exercise for you. Geometrically, find an eigenvector of A. As in, find a vector that doesn't change direction, give a geometric argument for this. No algebra necessary. Okay, we've explored our geometric interpretation of our eigenvalues and then eigenvectors. Let's actually get a little bit more precise. So how to find them? How to find eigenvalues. There will be multiple ways to do this, so let's just say that this is part 1. All right. So let's just walk through some things in order to make our next steps more obvious. Say lambda is an eigenvalue of A, then there exists a non-zero x vector such that ax is equal to lambda x. Okay, let's do a little bit of algebra. Ax is therefore also going to be equal to lambda times the identity matrix x. I can bring this over to the left side of the equation. Minus lambda ix is going to be equal to the 0 vector. And then we're going to have a minus lambda I, by just factoring out the x is equal to 0. Let's pay attention to this matrix. Notice, all of this means that x is a non-trivial solution to a minus lambda I x is equal to 0. This means, by definition, that x is in the null space of the matrix A minus lambda I. That means, of course, if a non-zero x exists, such non-zero x exists, this means that the determinant of A minus lambda I is going to be 0. Okay. Definition. Before we do some examples, n a minus lambda I is the eigenspace of A. The eigenspace of A corresponding to the eigenvalue lambda. That's because anything in this null space will be an eigenvector corresponding to lambda. Let's do some examples. Example. Say A is the matrix 2, 4, 3, 3. All right. Then A minus lambda I is what we're interested in. This is going to be 2, 4, 3, 3 minus the matrix with lambdas down the diagonal and zeros elsewhere. The determinant of A minus lambda I, well, this is going to be the determinant of the matrix 2 minus lambda, 4, 3, 3 minus lambda, which is 2 minus lambda times 3 minus lambda minus 3 by 4. All right, this is 6 plus lambda squared minus 5 lambda minus 12. If you FOIL it out, this is lambda squared minus 5 lambda minus 6, which factors into lambda minus 6, lambda plus 1. The eigenvalues are going to be the roots of this. So lambda is equal to 6, or lambda is equal to -1, and these are the eigenvalues. All right, here's an exercise for you. Find the eigenvalues of the matrix A is equal to 1, 2, 1, 4. In general, for an n by n matrix A, we expect the determinant of A minus lambda I to be a polynomial in lambda of degree n. The lambdas that make this 0 will be the lambdas for which there exists an eigenvector. The eigenvalues will therefore be are the roots of this polynomial. This polynomial is therefore important enough to have a name. Definition. The determinant of A minus lambda I is equal to 0 is called the characteristic equation of the matrix A. Notation P sub A with lambda in parentheses is equal to the determinant of A minus lambda I is called the characteristic polynomial of A. Let's do an example to make these terms clear. Example, from what we did above, for A is equal to 2, 4, 3, 3, the characteristic polynomial is going to be this polynomial, lambda squared minus 5 lambda minus 6, the roots of which were the eigenvalues. And the characteristic equation is just setting this equal to 0. Lambda squared minus 5 lambda minus 6 is equal to 0. Think on these things. Talk to you next time.